Hello and welcome to yet another question where we are working on two-phase method. So in last lecture we talked about the two-phase method in detail. Here we'll again sum it up, summarize it in a very brief way, and then we'll solve a question to see that even two-phase is not so much different from our simplex method, and in fact it simplifies our calculations on that we used to make in simplex. So here when we start in two-phase method, what we do is we make an auxiliary function. Auxiliary function is a function which we make out of the objective function. What is objective function? When we try to solve a simplex, objective function is an equation, a relation between all possible variables that we are making use of. The variables that we make use of are decision variables, slack variables, surplus variables and artificial variables. So objective function includes all these variables. Now we have certain rules for this inclusion. The rules are that decision variables take the values from the given problem, x1, x2, 2, x1, 3, x2, whatever is the problem. Slack and surplus are always multiplied with 0 to remove their effect. And artificial variables are dealt in such a way that I just use them for an initial start, and as soon as I start my problem gets started, as soon as artificial variables become outgoing variables, I forget the artificial variables. So this is the procedure for objective function. For auxiliary function, what we do is we make coefficients of all variables equal to 0 except for artificial. Coefficient of decision variable will be made 0, coefficient of slack and surplus will be made 0, and coefficients of artificial will be made 1. Now if it is a minimization problem, it will be made plus 1. If it is a maximization problem, our coefficient of artificial variable will be made minus 1. For max it is minus 1, for min it is plus 1 in auxiliary function. So we'll formulate our, we'll put up our question over here, then we'll solve it using two-phase method. One more thing, when your first phase comes to its conclusion, in first phase we have a two-phase method, first phase and second phase. When your first phase concludes, if any of the artificial variables still remains in the problem, like in previous question we saw when first phase concluded, A1 and A2 were kicked out. Now when first phase is ending, when first phase concludes, if A1 or A2 or A3, any of the artificial variables still lives in the problem, then we say that the problem does not have a feasible solution. If artificial variable survives, if artificial variable survives at the end of first phase, we simply say the given problem does not have a feasible solution. That we will see when we come across such a problem where the given problem does not have a feasible solution. For now, let us take a practice question, a small one. We will run through it and see the steps and phases. The question goes like this. Again, we have taken this question earlier in other methods. (40x1 plus 60x2) subject to then we have 2x1 plus 2x2 greater than equal to 50, and of course then there are non-negativity constraints or physical constraints as we may call them, that x1 and x2 cannot go below 0. They have to be either greater than or at most they can be equal to 0. They cannot go beyond 0. So this is our problem that we'll solve today using two-phase method. Now why do we need to go for two-phase? Because there are greater than inequalities. Now two-phase is not such a situation that every simplex problem you will go for a two-phase method. Two-phase is only used where we come across an artificial variable. Whenever you come across an artificial variable, when do you come across an artificial variable? When the inequalities are of these two kinds. Constraints. When the constraints are of greater than type or equal type. When you have these two kinds of constraints, then you go to either big M method or two-phase. Whenever you come across these kind of constraints, greater than or equal to, you go to artificial variable. And whenever you go to artificial variable, you need to pick one of the two methods, either big M method or two-phase method. Fine. So now, because these are greater than type inequalities, there will be a surplus variable which will be negative. That surplus will be countered with the help of an artificial variable, and because we have an artificial variable, we either need to go to big M method or two-phase method. These days we are practicing two-phase. We have talked about big M in detail in other lectures. So today we will solve it using two-phase. Now if you remember, what is our first phase? First phase is converting inequalities into equalities. We get x1 plus 3x2 minus s1 plus a1 is equal to 60. Because this was greater than, I deducted something, surplus. Now because this is a negative surplus, surplus is always negative, we put up an artificial variable. Then second one would become 2x1 plus 2x2 minus s2 plus a2 is equal to 50. Inequalities have been converted into equalities. Now the auxiliary function. What will be my auxiliary function? Zmin is equal to, now ideally the objective function would have been 40x1 plus 60x2 plus 0s1 plus 0s2 and some form of a1, and this is minimum, so I would have made it. Now if it were big M method, this would have been my objective function and I would have solved it using simplex if it were big M method. But right now we are not practicing big M method, rather we are practicing two-phase. So first thing is there will be no big M's, and second is that coefficients of x1 and x2 will be 0. Coefficients of all elements are 0. May it be slack, surplus or decision variable. Decision, surplus, if there were a slack it would have been 0. And what will be the coefficients of artificial variables? Because it is minimization, it will be plus 1. If it was a maximization, it would have been minus 1. For now it will be, the coefficients are 1. This is my formulation of the problem. This is my conversion into standard form. From canonical I have moved into standard form. Now can I find out IBFS? IBFS would be making x1, x2, s1 as 0, I get a1 as 60 and I get a2 as 50. This is my IBFS. Now can we have our first initial simplex table? Theta B A2, A1, S2, S1 all are coming in this table. And contributions are 0, 0, 0, 0. Contributions are 0 for all except for artificial. These will become 1, 1. IBFS is A1 is equal to 60, A1 is equal to 60, A2 is equal to 50. These are the contributions. And now can I have my Zj over here? And net evaluation, because it is minimization, net evaluation will be Zj minus Cj. Net evaluation row will be Zj minus Cj. It will not be Cj minus Zj. For max it is Cj minus Zj, but we are talking of min, so it will be Zj minus Cj. What are contributions of A1 and A2? 1 and 1. Now, can we fill in these equations? Let me fill in these equations over here. We have a 1, 3, minus 1, 0, 1 and 0. Then we have 2, 2, 0, minus 1, 0 and 1. And then we can find out Zj. Zj is sum product of every column respectively with contributions. Sum product of every column respectively with contributions. 1 into 1, 2 into 1. So 1 plus 2 would be a 3, 3 plus 2 would be a 5, minus 1, 1 and 1. This becomes Zj. Minus 1 into 1, 0 into 1. Minus 1 into 1 is minus 1 plus 0. 1 into 1 plus 0. So we have Zj. Then we can go for Zj minus Cj, which will be 3 minus 0. 3, 5, minus 1, 1 and 1. So two of the terms are negative. You can forget them. A lot of terms are positive also. This will be 0. 1 minus 1 would be a 0. So you can forget the negative and 0 terms. We'll talk of positive terms, and most positive. Most positive is, this becomes my key row. So now I have my key row. I need to decide upon my key column. How do we decide upon key column? We divide the B with A. B upon A and select the least positive. 60 upon 3 would be a 20. 50 upon 2 would be a 25. This is the least positive. So I get my key row. Sorry, this is not key row, rather this is key column. So I have my key column, I have my key row. And I also have my key element. The rule is to transfer these elements to a new matrix, dividing all elements of key row by key element. The rules I'll again put up over here. This time I'll put over here. First is first rule is for key rows, which is divide all elements of key row by key element. And second rule is old row I minus key column element I multiplied by modified key row is equal to new row I. We'll make use of these two rules. First, let us transfer the key row. For transfer of this key row, let us make a matrix over here. We have x1, x2, s1, s2. Now a1 is outgoing variable because it is key row. So a1 is going out. A1 is going out. I'll not be talking about a1 from here on. I'll directly be talking about a2. And a1 is moving out, and who is moving in? x2. So I can say that x2 and a2. A1 has been replaced by x2. A1 has been replaced by x2, and then a2 is intact. What are the contributions? We have 0, 0 for all variables, and artificial are having 1. x2 contribution is 0, artificial variable is 1. Now, divide all elements of key row by key element, giving me 1 by 3, 1, minus 1 by 3, 0, and a2 would be a 0 by 3, making it 0, and last one would be 20. This is how we bring the key row to our new table. Second rule is old row I minus key column element I. Old row I. Second, old row 2. The formula becomes old row 2 minus key column element 2 multiplied by modified key row is equal to new row 2. Old row 2. Old row 2 is this one. We have a 2, 2, 0, minus 1. 2, 2, 0, minus 1. Remember, A1 we are ignoring from here on because A1 has become outgoing variable. As soon as an artificial becomes outgoing, we forget it. So we have a 2, 2, 0, minus 1. Ignore this because it is out. 1 and 50. 1 and 50. Then we have key column element 2. Key column element 2. Multiplied by modified key row. Modified key row is this one. Negative would adjust over here. We have a 0, 0 and 20. Giving me 50 minus 40. 10. 1 minus 1. 2 by 3. 0. 6 minus 2, that is 4 by 3. So what do we get? We get a 4 by 3, 0, 2 by 3, minus 1, 1 and 10. This is our new row, second new row. Now let us have a quick check of identity matrix. A1 and A1 is 1, remaining column is 0. A2, A2 is 1, remaining column is 0. First was okay. Second one is X2, X2 is 1, remaining column is 0. A2, A2 is 1, remaining column is 0. So it looks like everything is on track for now. This becomes Cj. We can have Zj, then net evaluation would be Zj minus Cj. Zj, sum product of row with contribution. Now this is 0, so all these will become practically 0. So this will become my Zj. 1 into 4 by 3. 4 by 3, 0, 2 by 3, minus 1 and 1. So now I have my Zj, Zj minus Cj. This minus this. 4 by 3, 0, 2 by 3, minus 1 and 0. So this is 0, this is negative. They are out of discussion. What about this is also 0. This is somewhere around 0.66 while this is 1.33. So this is most positive. Most positive gives me my key column. And dividing B by key column, I'll get my key row. My outgoing variable x1 is the incoming variable for now. X1 is the incoming variable. This is my key column. 20 divided by 1 by 3. 20 divided by 1 by 3 making it 20. This gets flipped. So you get a 60. 10 divided by 4 by 3. 10 divided by 4 by 3 making it 10. This gets flipped to 3 by 4 making it 30 by 4. 7.5. So now I have my key row also. Least positive gives me my key row. And intersection of key row and key column will give me my key element. So now we can move on to our next matrix. As we have our key column, incoming variable, key row, outgoing variable. X1 is coming in place of A2 this time. B and theta, X1, X2, S1, S2. Now A2 is outgoing variable, so A2 will also be ignored from here on. Contributions for each of these are 0. X2 is intact. A2 is being replaced by X1 with respective contributions of 0 each. Now, the first rule, divide all elements of key row by key element. This is my key row. Divide all these elements by key element. 4 by 3 upon 4 by 3 would be a 1, 0. This would become a 2 by 3 divided by 4 by 3. 3 cancels out, it becomes 2 by 4. So we could write it as a 2 by 4, or we could put it down as a 1 by 2 also. And then this would become a minus 1 upon 4 by 3. Divide all elements by key element. Minus 1 into 3 by, making it minus 3 by 4, and last one would be a 30 by 4. You could put it down as 30 by 4, or you could also call it 15 by 2. So we have transferred our key row. Now let us transfer the first row. Old row 1. Old row 1 minus key column element 1 multiplied by modified key row is equal to new row 1. My row is 1 by 3, 1 minus 1 by 3, 0. Remember, A2 will be ignored. So I only take 1 by 3, 1 minus 1 by 3, 0. This is ignored, and 20. Key column element 1. Key column element 1, which is 1 by 3, multiplied by modified key row. Modified key row, here we have our modified key row. What is it? 1, 0, half, minus 3 by 4. So minus will adjust over here, and you will have with the 3 by 4 and 15 by 2. So what does this become? 0, 1. This will become a minus 2, minus 1. That is minus 3 by 6. Minus 2, minus 1, minus 3 by 6. Or you could call it a minus half. 3 cancels, it becomes a 1 by 4. 6. Making it 120, making it 105 by 6. So we get 0, 1, minus half, 1 by 4 and 105 by 6. Now let us find out Zj and net evaluation row, that is Zj minus Cj. All getting multiplied by 0, 0 plus again a 0. So all these will be 0. And then Zj minus Cj, 0 minus 0, 0 minus 0. Now, as we see that the complete net evaluation row is either 0 or negative, in our case it is 0. So, we can say that this is end of phase 1. Why end of phase 1? Because we were not working on our original function, rather we were working on an auxiliary function. So, I can say that this is end of my phase 1. In phase 1, we had first table, second table and third table. Now, because this is end of phase 1, we can move to phase 2. How do we go to phase 2? We keep all these matrix values intact. We just replace the auxiliary function with the original function. So, our phase 2 would be x1, x2, s1, s2, b and theta. Values would be 0, 1, minus half, 1 by 4, 105 by 6. Then we have a 1, 0, half, minus 3 by 4 and 15 by 2. Here we have x2 and x1, x2 and x1. So we have complete matrix copied to a new matrix, but this time round, instead of these auxiliary values, I will be having the original values, that is 40 and 60. 40, 60. Obviously, slacks and surpluses are 0. Contributions x2 is 60, 40. So now I have my Cj, I can have Zj, then I can have Zj minus Cj. Why are we going for Zj minus Cj? Because it is a minimization problem. So let us find out 0 and 40. This will become a 60 plus 0. Then this will become minus 30 plus 20 minus 10. And finally this will be 15 and this will be minus 30. Plus 15 minus 30 making it minus 15. Zj minus Cj. 40 minus 40. 60 minus 60. Minus 10 minus 15. All values are either 0 or negative. Hence, this is my final solution. What is my final solution? X1 is equal to 15 by 2. X2 is equal to 105 by 6, giving me a value of Z 40 X1 plus 60 X2. 40 X1 is 15 by 2, 60 into 105 by 6. If you further solve it, you get 20, making it 300. This becomes 10, making it 1050, making it 1350. So I get the value of Z of 13. This is my minimum possible solution for 40x1 plus 60x2. Now, the same problem can be done using big M method also, and same problem can be done using two-phase method also. When I start my first phase, I start with an auxiliary function. I proceed. I see that net evaluation row reduces to either 0 or negative, so I stop over there. When I stop over there, I check if artificial variables still live. If there is an artificial variable, I stop and say that this problem cannot be solved. It does not have a feasible solution. But because my present solution, my final solution is free from artificial variables, I advance to the second phase. Second phase takes up the same table and updates the contributions to the real contributions, the natural contributions that were given. And then we check. More often than not, this is our final destination. Otherwise, in a table or two, this finally solves it. So now, again, I see that all values are 0 or negative in the net evaluation row. So I say that this is final solution. X2 is equal to 105 by 6. X1 is equal to 15 by 2. This was it for our today's practice question. Next time when we meet, we'll take a maximization case. We'll take a maximization case with both types of inequalities, less than and greater than. So up till now we have practiced minimizations with greater than for two phase. Next time when we meet, we'll take a maximization question with less than type inequalities and greater than type inequalities. So this was it for our today's lecture, and thanks for watching. Bye bye. Take care.